Hello, one and all. I'm Farhan Heather, and welcome to a short talk on impacts of UC formulation tightening on computation of convex hull prices. This work was jointly done by researchers from Rochester Institute of Technology and University of Connecticut. To understand our work better, let's go over the background information. The state of practice in US electricity market is to set prices by solving the economic dispatch problem, with commitment decisions fixed at optimal values from the UC problem. Although this method is easy, it however does not take into account fixed costs such as startup and no-load cost, which in turn requires the ISO to pay large uplift payments as compensation to generators who may have lost an opportunity to gain higher profits. When we do include the fixed cost, we notice that the marginal prices are not monotonically increasing with the load. The figure on the right shows total cost versus load, and the curve is the cost function. The slope to the curve gives you the marginal price, and as you can see, the marginal price is not monotonically rising. One approach to overcome this challenge is convex hull pricing. There are two ways to get the convex hull price. The first one is using the slope of the convex envelope of the total cost function. Here, the red curve represents the convex envelope, and its slope gives you the convex hull price. And you can notice that the slope of the convex envelope rises monotonically with the load. However, this method is challenging as it's very difficult to obtain the convex envelope of the cost function. Another approach to calculate the convex hull prices is using the dual variables associated with the system demand constraints of the UC problem. This method suffers from convergence difficulties and long solving time. Therefore, in this paper, we choose the second approach and try to overcome its difficulties using decomposition coordination methods and formulation tightening. We use a decomposition and coordination method called surrogate Lagrangian relaxation for fast convergence. We use formulation tightening of the subproblem for reduction of computational efforts. Finally, we try to study and understand the impact of formulation tightening on computation of convex hull prices, and which are being solved by SLR method. Let me now explain the motivation behind our approach. Up first is the impacts of formulation tightening. The idea is that tight constraints directly delineate the convex hull of the feasible set, and the optimal solution to the LP problem is also optimal to the MILP problem. Let's consider the original formulation, which is not tight. The solution to the MILP problem is X star, but the solution to the LP problem is different from X star. However, if the formulation is tight, represented by the red lines, the solution to both the MILP and LP problem is X star. Hence, we can use integer relaxation to get the same optimal solution. We use the constraint vertex conversion process to get tight formulations. You can learn more about it in one of our previous studies. In practice, however, it's very difficult to obtain tight formulations for individual units for 24 hours. Hence, the goal is to obtain tightened formulations. The green lines represents the tightened formulation. Its optimal, its LP optimal is very close to the MILP optimal, but not exactly the same. However, its LP optimal is a lot better than the original formulation. Hence, we get approximate optimal solutions. The idea behind choosing SLR method was to overcome the major difficulties of traditional Lagrangian relaxation methods. The surrogate Lagrangian relaxation method does not need us to solve all subproblems. It reduces the multiplier zigzagging, and it does not require the optimal dual for convergence. Let me now discuss the implementation of our idea. We use the IEEE 118 bus system for testing. The performance of our Titan UC formulation is compared with the conventional two-bin formulation, where both formulations are solved by SLR method. The first experiment is a 3-hour example whose results are shown in the table. The MILP conventional and MILP tight are used to calculate the convex hull prices. Upon integer relaxation, we notice that the LP conventional formulation cannot give us the convex hull prices, as it produces different prices from the MILP conventional. However, upon integer relaxation, the tight formulation gives us the exact same prices, which are the convex hull prices. Moving to our 24-hour example, its results are shown in the figure on the right, where the blue markers represents MILP conventional, the orange markers represent the LP conventional, and yellow markers represent LP tightened formulation. The prices from all these formulations. So you can notice that the yellow markers closely follow the blue markers, but the orange markers do not follow the blue markers that closely. This shows that upon the relaxation, the prices obtained from the 24-hour tightened formulation are very close to the actual CHPs, hence they are good approximation for the conventional prices. However, the same cannot be said about the LP conventional. Conclusion. In this study, we understood the impact of formulation tightening on computation of convex hull prices by comparing the performance of our tightened formulation with a conventional tube-in formulation and solving them by SLR method. All experiments were performed on the IEEE 118 bus system, and the results show that upon integer relaxation, prices obtained with the 3-hour tight formulation are accurate convex hull prices, and upon integer relaxation, the prices from the 24-hour tightened formulation are very close approximations to the actual CHPs. This demonstrates the potential of formulation tightening on computation of convex hull prices. These are the key references, and thank you for listening.